ABC Calc day 29. Take a look. It's a review. I'm going to do a lot of the review in today's notes with you, and then anything that we don't wind up getting to, of course, we'll recap the next time I see you in class. As you can see, we've got a quiz coming up. Day 30 is technically going to be our next quiz, and what's going to be included on it? Well, all the things we've been working on. A lot of this was included on that day 28 practice that hopefully you're just about finished with, or if not, we'll be finishing up soon. But we've got things like Newton's method, quadratic approximation, and the max error that is associated with those approximations, curve analysis and sketching, continuity and differentiability, max-mins, velocity and acceleration, and some quick practice with definition of derivative. So when you look at this list, a lot of the focus will be on some of the more recent topics, but you can see how other topics sneak their way in there, like definition of derivative, continuity and differentiability. Pretty much every quiz we have this year will have some element of a cumulative nature to it, where we kind of bring in some older topics. So we want to make sure we're staying fresh with those concepts there. We've done questions like this practice before. So what I'll encourage you to do is, even though I'm about to go through these right now, why not hit pause and try them real quick? And of course, it's really up to you how much you want to try and get some practice on your own. But I'll model the examples that we're going to go over right here. And if you think you know how to do them, hit pause and try them right now. So what we have going on here is that we have these limit definition of derivative examples. And certainly I don't want to, looking at this bottom example, expand this out to the 12th power and try and simplify to find what's going on in terms of this limit. It's going to take forever. So we want to recognize this as the derivative of a function that we know, and specifically in these examples, it's the derivative at a given value of x. So when I have this quantity squared, 2 plus h squared minus the quantity 2 squared, we're looking at the derivative of the function x squared at x equals 2. And we've done this maybe already where we put x's in those locations instead of 2's. But if I replace those x's with 2's, it's just the concept of finding the derivative at that given value of x. Well, the derivative of x squared is, of course, just 2x, and therefore f prime of 2 winds up being 4. So the final answer, without doing any sort of expansion there or simplifying, we can really quickly justify that the answer is 4. Similarly for number 2, could we do some algebra and eventually evaluate that limit as h goes to 0? Of course, but it's going to be much quicker to recognize that the original function that we're trying to find the derivative of, it would be for this quantity, just call it x squared minus 2x plus 1. And we're finding the derivative at x equals 3. So f prime of x would be 8x minus 2. And therefore, f prime of 3, well, 8 times 3 is 24, minus 2 is 22. And finally, last but not least, this would have been crazy if we had to expand this out to the 12th. Nobody wants to do that. So recognizing that this is the original function, x to the 12th power, and we're looking to find the derivative at x equals 1. So f prime of x is going to be 12x to the 11th, and therefore f prime of 1. 12 times 1 to the 11th is 12. So these wind up going fairly quickly if you can easily recognize the function we're taking the derivative of, and if it's at a specific value of x. Once we find the derivative, sub that value of x in, and we are good to go. All right, so that was the first page of just some quick practice questions here. On the next page, we're talking about some ideas behind finding roots, and there are lots of different ways that we can find roots from pre-calc honors and even algebra 2 honors. We can find roots in many different ways, like maybe the easiest technique is, if possible, use some factoring. So this one does wind up being factorable. If I break this into x minus 4 and x minus 2, I can find the roots, but even if we have something that's not factorable, we have other techniques we can use. For this one, if it's not factorable, how about something like quadratic formula? Are you guys singers of quadratic formula? Do you do x equals negative b, which is positive 3 plus or minus the square root? I can't help but sing it. Of negative 3 squared minus 4 times 2 times negative 7 4ac all over 2a, 2 times 2. All right, so you can easily sub into quad formula if we need to find roots. And why are we even recapping this? We're talking about, if we're thinking about curve sketching and things of that nature, finding the roots and x-intercepts are going to be critical values to include in an accurate sketch. For something like h of x, if you have cubic polynomials and higher, you would have learned these tricks and tools in Algebra 2 honors and recap them in pre-calc honors. Do you even know what these things mean? Maybe you do. Maybe you're shouting them from the comfort of your own home right now. How about like Descartes' rule of signs and rational root theorem and synthetic division? All those things might help you to find roots of cubic polynomials and higher, right? They're kind of all these tricks and tools that can help me find possible rational roots to test by using synthetic division. I'm convinced actually for this one, we probably don't need any of those tools because this is factorable if you take out an x squared and use some factoring by grouping. You actually can develop the roots fairly quickly if we use that technique instead. But know that this is still out there, right? Now, keep in mind that this is really only out there when I talk about RRT, which is the rational root theorem. It's only out there if this cubic has a rational root. If it doesn't have a rational root, we're in trouble. So there we go. Hence Newton's method. So let's go through another iteration and practice of Newton's method here, trying to determine roots of a given polynomial. We're going to work on the polynomial f of x equals x cubed minus x plus 1. And I've written down what Newton's method is for you off to the side, that we're generating the next term in the sequence by taking the term prior, subtracting f of that x sub n, and then the derivative at x sub n. Remember, the way we derive this is we're looking at the x-intercept of the tangent line. So when we consistently find new x-intercepts for the next tangent line and ping pong back and forth, it becomes a recursive sequence, and we can use this to model it. So if I go ahead and make a quick sketch here of x cubed minus x plus 1, let's check out and see what it looks like. X cubed minus x plus 1. Okay, so I'm going to zoom 6, see what this looks like, because we need to have that initial guess. Okay, we're going to use the calculator to figure out that the initial guess probably, we should guess something like x equals -1 according to where I see this cross the x-axis. If I were to make a sketch, we have something that looks like this. So to find this root, I think it would be reasonable in this instance to say, you know what, let's make our initial guess. -1. And if you don't guess -1, if you were to guess, let's say -2, you should be able to also, after a certain number of iterations, get a really nice amount of accuracy that we desire to get the approximate value for that irrational root. So we already have typed into y1 the function x cubed minus x plus 1. In y2, in order to run through our Newton's method iterations, we need the derivative of what we have in y1 for all x values. And what we're going to do is we're going to initially store this value. We're going to do -1 and store it as x. So if that's our initial guess, what we're going to do is we're going to take that value of x and then do f of that x value, which is just taking y1 there, over the derivative at that value of x, y2. And whatever that number comes out to be, that's the next x-intercept that we're looking at. So I want to store that as x. And once that gets stored as x, if I keep hitting enter and doing this again, it's going to take my new stored value of x and run through this process, which is pretty awesome. So let's go ahead and make sure in y2 we have the derivative entered in there. So we've got math 8 of y1. And again, the trick there is alpha trace if you want to get y1 quickly at x equals x. If we quit that screen, we're going to do that -1 is stored as x. And then we want to do x minus fancy fraction y1 over y2. And we want to take that and store that as our new guess, our new value of x. So when I run through that for the first time, here's what Newton's method tells us, is that for n equals 1, we get -1.4999975. And then all you have to do is keep hitting enter. So what we did was we took this, stored it as x, such that when I run through this iteration again, we're now using that new x-intercept, that new root that we're testing. So now we've got negative 1.3478260054. Keep going. For n equals 3, we get negative 1.325200403. So what we're looking for is for two successive approximations to differ by usually less than 1/10,000th. It will be specific enough on the test that you will know when you should stop with your approximations here. So 324718174. Probably usually don't go much past 5. Let's see what this says. Negative 1.324717957. So I think we're pretty good at to stop there, since these two differ by less than 1/10,000th at this point. Okay. So if you have any questions about Newton's method, of course, you'll be able to check in with me about that. Remember, Newton's method is not only good at finding roots, we can find intersection points among functions by subtracting one function to the other side and setting it to 0 and thinking of it as a root application. So if we're good with Newton's method, I am going to try one more question with you. And again, of course, everything today, because it's a review, is fair game. If you're like, no, Mr. All, I don't want to see it yet, hit pause right now and take a blast from the past and head back to the 80s for this question right here. So it's a good old trig curve sketching question. So it says, find the x-intercepts of the graph of f. Find the x and y coordinates of any relative max points, find where it's increasing, and then take the information and make a sketch. It's important to note here that we're looking at this function f of x over the interval from negative pi to pi. So to find the x-intercepts, first and foremost, we've got to set our function equal to 0. And when I do that here, we're going to take out a GCF of cosine x, and that leaves me with 1 minus cosine x. So we need to solve when does cosine x equal 0. And then over here, you would get when does cosine x equal to 1. Now, remember, this is over the interval from negative pi to pi, which is maybe not the most traditional interval that we look at this over. I feel like typically we're looking at 0 to 2 pi when we determine our solutions. But over negative pi to pi, what's going to happen for x equals 0 is you will get solutions at plus or minus pi over 2. All right, think about the cos curve from negative pi to pi. Here's negative pi and here's positive pi. We're looking at something that looks like this. Okay, so at negative pi over 2 and positive pi over 2, we definitely have zeros. And then where does cosine x equal 1? Well, only at x equals 0. So altogether, your x-intercepts are at negative pi over 2, 0, and then positive pi over 2. And those sound like important pieces of information to go ahead when we get down to part D there to make sure that we're making an accurate sketch. All right, part B, find the x and y coordinates of all relative max points of f. So if I'm talking about relative max, I better be finding some derivatives. So the first derivative, f prime of x, would be, derivative of cos is negative sine x. And then just don't forget about chain rule for minus cos squared x. So it's going to be minus 2 cosine x to the first times the derivative of the inside, which is negative sine x. So the derivative, if we kind of clean this up here, the negative times the negative could be written as positive 2 sine cos, if you want to do some quick rearranging there, with a minus sine x that follows. Okay, so in order to find relative extrema, we know that, of course, we're going to set our first derivative to 0 and find those critical points. And then nicely here, our derivative has a GCF of sine x. So if I factor that out, that leaves me with 2 cosine x minus 1. So we're going to set sine x equal to 0. If I solve when 2 cos x minus 1 equals 0, we get cos x equals a half. So when does sine x equal 0? And again, maybe you're a curve person, maybe you're a unit circle person, but sine x equals 0 at pi, at 2 pi, and oh wait, we don't even want to go to 2 pi. We kind of want to go backwards from there, if anything. This would be solutions at negative pi, 0, and pi. Okay, negative pi and pi, of course, are the endpoints of the interval. So we'll go ahead and make sure that we plot those and test everything in between. And then for cos x equals a half, if we're trying to be exact here, we know that cosine's positive in 1 and 4. If it's adjacent over hypotenuse, we get this reference triangle whose reference angle is going to be pi over 3. Now, remember, we don't really want to say 5 pi over 3 is the other solution. We want pi over 3 and negative pi over 3. So plus or minus pi over 3 are going to wind up being critical points to partition around as well. So when I go to set up my f prime number line, we got negative pi and pi as the endpoints of the interval that we're graphing over. And then we need negative pi over 3, 0, and then finally pi over 3. And in terms of the testing and doing the partitioning here, just make sure that when you're substituting in, that you're choosing appropriate values in each of these sections. I would be smart and probably try and choose things like pi over 6, which is in between 0 and pi over 3. Over here, I might choose something like pi over 2, easy values for me to be able to sub in and be able to evaluate in the derivative, okay? So just as a quick example, if I choose pi over 2, sine of pi over 2 is 1, but cos of pi over 2 is 0. So all of a sudden that becomes 0 altogether. And by the way, you can also use this factored form as well, right? And then minus sine of pi over 2, well, sine of pi over 2 we said was 1, but it gets negated. So between pi over 3 and pi, we get that that's negative. So we know we're decreasing here. If I test pi over 6, sine of pi over 6 is definitely positive. What's cosine of pi over 6? It's radical 3 over 2, so those 2's would cancel. And radical 3 minus 1 is also positive, okay? So we have to have, I think, some really good trig sense here to make sure that we can quickly substitute in to the factored form or the original, doesn't really matter. But to save me just a little bit of time, and I don't know why I'm necessarily working backwards here, but it's probably easier for us to think of the positive angles first anyway. So we're going to get that these signs do wind up alternating here. So over the interval from negative pi to pi, it looks like we're going to have a relative max at negative pi over 3 and also at positive pi over 3. Okay, are those absolute max coordinates? Maybe not. I guess we'd have to check the endpoints as well. But we know that we have relative max at, well, if I plug in negative pi over 3 for the original, remember that cosine of negative pi over 3 is going to be a positive quantity. Cosine's positive in quadrant 4. So cosine pi over 3 is a half minus, then over here you're going to get cosine negative pi over 3 is 1/2 squared. So a half minus a fourth winds up being a fourth. And you get the same thing if you plug in positive pi over 3. So I'm going to write the coordinates as plus or minus pi over 3, comma, 1/4. Okay, boy, am I relying a lot on our trig knowledge and skills to be able to evaluate quickly at those given values of x. Okay. For part C, increasing, you know what? We've already done all the tough work, haven't we? It's increasing over these two intervals from negative pi to negative pi over 3. And then from 0 to pi over 3. And then last but not least, using all of this information, we should be able to make a really nice sketch. So I'll do part D over here, over the interval from negative pi to positive pi. I'd probably want to figure out over that interval where the starting and ending points are, right? So cosine of pi winds up being -1 minus -1 squared. Well, -1 squared is 1, so -1 minus 1 is it's actually -2, right? And the same thing will happen when you plug in negative pi. So here are 2 points that we definitely know are on the curve. We have some relative max values. Oh, by the way, we also have some x-intercepts. So we can put those 3 x-intercepts here. And what you'll find when all is said and done is that this does have some really nice y-axis symmetry. So negative pi over 3, comma 1/4. And then positive pi over 3, comma 1/4. So something like that. So we're going to get a graph that looks like this. Okay, so over that closed interval from negative pi to pi, here is what the graph of cosine x minus cos squared of x looks like. Okay. So yeah, definitely a lot of work involved behind the scenes here, and we have to really rely very heavily on some of those pre-calc skills to be able to have a good foundation of the trigonometry with special triangles, unit circle, graphs, whatever we need to get there. So if you have any questions about this, you'll let me know next time I see you in class. But I am going to make this a traditional try at this last one. So I think we probably could benefit from some more practice with curve sketching in the sense of given a graph of the function's derivative is what this is. This is f prime of x, which it says it in a few places if that's not clear. So given the graph of f prime of x, see if you can answer the following questions. We should be able to, hopefully with ease, determine relative max and min points. If you're not somebody who's traditionally like, yeah, I'm going to try it on my own, definitely try this one. There's not a lot. I mean, it does say to justify why, but it's not going to be that much of a challenge given what we've done so far with curve sketching. Okay? So give this one a shot. We'll go over it next time I see you and get ready for our next quiz that is upcoming. Thanks. Have a great rest of your day. Let me know if you have any questions.